Imagine staring so far back in time that the first galaxies flicker to life, only they are brighter, denser, and older looking than the universe's script allows. This is the riddle James Webb has handed us dust, before time stars born in fast-forward spectral whispers of earlier cycles and gravitational lenses ticking like clocks that sometimes disagree with the calendar. Simulations strain constants are questioned, and new telescopes gather at the horizon to decide, did the cosmos build faster with familiar tools pushed to their limits, or is there a hidden preface and echo before the overture? Tonight we follow the earliest light to the edge of certainty, where intrigue becomes measurement and mystery turns into a map. The telescope stares into a darkness that is not empty but crowded with whispers, and in the deepest fields where integrations stretch through weeks, faint structures rise like embers breathed back into glow. Photons that began when the universe was only a few 100 million years old arrive with colours pulled long by expansion. Redshift. The measure of that pull turns colour into time and lets observers arrange a chronology at the edge of visibility. There, galaxies appear both brighter and smaller than the script expects, knots of light pressed into tight radii, luminous enough to be noticed in exposures designed to find only the shyest glimmers. The first impression is a paradox wrapped inside a survey at distances where theory sketches tentative beginnings. The images hint at practiced hands. The signal does not shout, it accumulates. Stack by stack, hour by hour, the background smooths into velvet, and on that velvet the tiniest pricks of light hold their shape, refusing to disperse back into the noise that birthed them. NIRCam sketches the outlines with a method that is both simple and unforgiving. Filters tuned across the near-infrared sift, the ancient light and objects that vanish in the bluest filters but persist at redder wavelengths, mark themselves as extreme redshift candidates. These are pillars in a fog present, precisely by the way they hide. Catalogues bloom, and with them a careful unease. The counts look high. The sizes, when fit with cautious profiles, contract to half-light radii, measured in only a few hundred parsecs. Such compaction is not an aesthetic flourish. It implies densities and star formation intensities that models trained on a slower dawn rarely allow. If feedback from young stars and supernovae should tear early galaxies apart, these sources seem content to ignore the instruction. Some may be gently magnified by intervening structure, but magnifications inferred from mass maps and shears tend to be modest, insufficient to turn a sparse universe into a crowded one. The uneasy question rises with the tally: has the schedule slipped, or was it written too conservatively from the start? Spectroscopy turns hints into sentences, where imaging teases with colour spectra speak in lines and breaks. NearSpec opens a shutter and finds features at the very places the photometry predicted. Oxygen and helium lines whisper of hot stars busy with fusion. Abrupt discontinuities between adjacent bands sketch out populations older than the youngest burst would allow. Each spectroscopic lock clicks onto a photometric key, and each click removes an easy escape. Foreground interlopers thin out. Miscalibrated filters lose credibility. The ladder from photometric guess to spectroscopic confirmation acquires rungs sturdy enough to climb, and with the climb comes a new vantage point. What once could be dismissed as selection bias begins to look like the sky's own preference. Around the sources, the canvas itself shows a subtle warp. Fluctuations ride the cosmic infrared background like a soft grain that careful stacking makes visible, aligning with the multitude of faint objects that the telescope can only half resolve. Low-level lensing along the line of sight complicates the arithmetic but rarely erases it. Convergence fields nudge the counts without transforming them. None of these influences is dramatic. All are stubborn. Together they suggest that the earlier structures are more abundant than the smoothest histories would like a conclusion uncomfortable, not because it is incoherent, but because it implies efficiency where reticence had been assumed. Against this calibration refuses to yield the villain. Pointing thermal stability and detector behavior are watched with a suspicion bordering on affection. Internal lamps reference stars and well-characterized fields confirm gains and flats. Cross-checks with Hubble, ALMA and Subaru narrow uncertainties until they behave more like punctuation than plot. The instrument remains grounded in nearby certainty, a crisp confidence in the way it measures planets, resolves rings, and dissects bright nebulae. That local clarity, instead of soothing the worry, sharpens it. If the ruler is straight close to home, then the crookedness belongs to the story written in the far light. What then does this first frame mean for time? If the distances are right, and the mass estimates survive conservative assumptions about stellar populations and dust, the path from initial conditions to these luminous knots must have been more efficient than expected. Perhaps cold streams fed halos with fewer interruptions slipping past feedback to deliver fuel directly to compact cores. Perhaps thresholds for star formation were lower in gas that cooled more cleanly, or the initial mass function tilted stacking early systems with massive stars that burn bright and fast. Each of these ideas leaves fingerprints, a ratio of lines, a shape to a break, a texture to a continuum that observers now scramble to collect. The field's excitement does not come from any single conjecture, but from the practical invitation to test conjectures in data that arrived earlier than anyone anticipated. Mitigations line up for inspection. Selection may favour the most compact and luminous, hiding a quieter majority. Lensing may be trickier than the first maps imply, gently inflating the event rate. Template spectra may bias fits toward older ages, and dust may lurk in amounts that redden light without revealing itself cleanly. None can be dismissed. None yet dissolves the simple statement that the early universe looks crowded with capable builders. The puzzle is not a single dazzling anomaly, but a mosaic of small resistances to the expected pace distributed across fields, instruments, and observing programs that were built to disagree with one another when they must. So observers do the most faithful thing the discipline knows they look again. Deeper integrations and wider mosaics are planned to trade inference for measurement wherever possible. Programs coordinate to catch the same sources with multiple instruments stitching spectra across broader baselines to pin down ages, metallicities, and ionization states. Gravitational lensing fields are canvassed to borrow magnification without inviting too much distortion. Time is requested not to confirm a rumor, but to enforce a standard to see whether every bright, compact candidate stands up under the full weight of scrutiny, or whether some quietly slide away as the noise floor sinks. The craft of patience honed over decades of sky surveys becomes the vehicle for urgency. Even as new data arrive, the freshness of the mystery outpaces the answers. On the scale of billions of years, a discrepancy of a few 100 million sounds modest. In the regime of first structure, it is everything. It is the difference between chemistry finding its first foothold and chemistry already recycling. It is the distinction between a dawn of scattered embers and a dawn of lanterns already lit. These first images do not foretell failure, they invite revision. They ask for a redrawn prologue so that what follows can be told without strain, whether that redrawing means accelerated assembly within familiar rules, or a gentle lawful shift in the rules themselves. The frame holds the points persist, and the narrative leans forward, aware that the earliest light has more to say than the current script allows. Instruments and anchors define the trust a field can place in its boldest claims, and the Space Observatory's chain of evidence begins with how every photon is shepherded from sky to archive. The near-infrared camera casts a wide and exquisitely sensitive net, and its filters, detector behavior and optics are characterized with a rigor that turns preferences into proofs. Intentional dithers slide the point spread function across different pixels so that fixed defects average away, while carefully modeled intrapixel response maps prevent brightness from depending on where a source lands within a pixel. Flat fields and dark current calibrations are refreshed and challenged by independent teams, and ramp-fitting schemes account for cosmic ray hits without distorting the underlying signal. The resulting mosaics are not only deep, they are stable exercises in metrology, where a source that appears compact in one visit continues to look compact when the telescope rolls, when the background changes, and when another team reduces the same frames with a different pipeline. The mid-infrared instrument adds a slower cadence view that catches cooler dust and nebular emission, and its repeatable photometry and well-characterized optical ghosts allow observers to disentangle true structure from artifacts. The near-infrared spectrograph then turns light into language. A configurable array of microshutters opens in custom patterns to select faint targets, and dispersers slice the stream into sequences of lines and breaks that carry composition and distance. Wavelength solutions are pinned to internal lamps, spectral standards and skylines captured in parallel slits so that each pixel corresponds to a verified interval in energy. Resolution and throughput are measured, not assumed, with repeated visits to the same stars and galaxies that reveal drifts if they exist. Spectra from independent gratings and orders are stitched with attention to slit losses and to the way light spills into wings, and the final extractions include robust variance estimates that matter as much as the flux itself. Large programs serve as proving grounds where these instruments are pushed from specification to practice. The Advanced Deep Extragalactic Survey builds an interlocking lattice of fields that are deep enough to expose the earliest galaxies and broad enough to sample variance. The Early Release Science Program on Cosmic Evolution offers the community rapid access to a transparent baseline that others can test, critique, and extend. The Lens Amplified Survey from Space points the observatory through natural magnifying glasses, letting the sky itself provide modest boosts that pull fainter, smaller sources across the threshold of detection without relying on extreme assumptions. Each program carries its own reduction culture, its own priors, and its own failure modes, and this deliberate plurality is an anchor when separate paths converge on the same objects with the same properties. Trust grows. Cross-calibration across facilities amplifies that confidence. The Hubble Space Telescope supplies overlap in filters and imaging that lets teams compare point spread, function shapes and photometric scales across the region where the two observatories meet. The Atacama Large Millimeter Array listens for coal dust and molecular gas-checking star formation rates, inferred from ultraviolet and optical light, against far-infrared reprocessing and constraining obscured components that might hide from shorter wavelengths. The Subaru telescope, with deep ground-based imaging and spectroscopic follow-up, ties photometric catalogues to alternative measurements of sizes and colors, and it maps lensing shear fields that inform magnification estimates. Where numbers agree to within uncertainties, the instruments interlock. Where they disagree, the difference becomes a diagnostic rather than a doubt. Precision lives not only at the center of a distribution, but also in its tails, and the teams go looking there. They probe detector behavior at the lowest count rates where read noise and subtle persistence can masquerade as flux, and they model the wings of the point spread function because compactness estimates depend on the balance between core and halo. They characterize charge trapping and release, ensuring that bright sources do not poison subsequent exposures with ghosts that could be mistaken for faint companions. They quantify pointing drift and thermal breathing, and show that these do not broaden images in a way that would bias size measurements towards small values. Every weakness an instrument admits becomes a number in a correction, rather than a rumour in a forum, and those numbers are remeasured as the mission ages. Reduction pipelines become instruments of their own, and are conducted like experiments. Flat field generation is varied to assess sensitivity to field choice. Sky subtraction strategies are rotated to check for bias when the background is structured by diffuse emission or scattered light. Forward modelling fits galaxy profiles directly in the image plane, injecting artificial sources into raw data to measure recovery rates and selection biases. Spectroscopic extraction is performed with multiple algorithms, and redshift solutions are cross-checked by independent groups that are incentivized to find disagreements. Photometric redshifts are constrained by template libraries that include young, dusty and metal-poor populations, and the consequences of each template choice are propagated into mass and age estimates with transparent priors. The measurement of distance is controlled not only by the presence of lines, but also by their meaning. The Lyman break created when hydrogen absorbs photons shortward of a specific wavelength remains a powerful selector at extreme redshift, but dusty galaxies at moderate distances can imitate that signature. Oxygen and helium emission at the predicted long wavelengths removes that confusion. Balmer breaks, which suggest older stellar populations, can also be produced by a mixture of ages and dust. Observers handle this by seeking multiple independent indicators that point to the same answer. The rule is simple and stern. A single path to a spectacular claim is not enough. Distinct paths must meet on the same coordinates. In parallel, the observatory proves its honesty close to home. In the solar system, photometry of moving targets matches heritage measurements from spacecraft and from ground-based surveys, once light travel time, motion smear and phase angle are accounted for. The stability of the thermal environment and the pointing translates into repeatable, point-spread function shapes that do not wander with solar illumination or with orientation. Planetary rings, asteroids and comets serve as live calibration fields where brightness ratios and spatial profiles can be predicted, observed and reconciled. Cross-checks with spectrophotometric standards and with white dwarf calibrators keep the absolute scale from drifting as seasons change. All of this culminates in repeatability. A candidate identified in one deep field is reobserved with a new roll angle and remains what it first appeared to be. A mass derived with one synthesis model is recomputed with a competitor and stays within a credible band. A size measured with one profile fit is tested with an alternative and shifts only within the quoted uncertainty. Time in orbit does not introduce creeping drifts. Familiarity improves precision. The wider the community that touches the data, the more resilient the result becomes, because hidden assumptions fail to survive a second culture of reduction. The field therefore approaches the earliest light with a ruler that has been checked at many marks. Instruments designed to disagree with one another when wrong now converge, and surveys designed to expose biases now see through them. The story that emerges is not a rush to proclaim anomalies, but a careful tightening of error bars around facts that have already proven reluctant to budge. Each observation in the deepest fields is backed by a lineage of calibrations, cross-checks, and independent reconstructions that collectively shrink the space where mistakes can hide. What remains after that space is made small is precisely the intrigue. The measurements look stubbornly solid, and the anchors hold fast even as the horizon keeps offering surprises. The redshift ladder is a sequence built from caution, where the first rung is a colour and the last rung is a line that falls exactly where physics says it must. Photometric selection begins with the language of absence. A galaxy appears in redder filters but disappears in bluer ones, and that vanishing argues for a steep drop in flux at the rest frame wavelength where hydrogen soaks up light. The near-infrared camera arrays the sky through a suite of filters that straddle this break, and candidates are sifted by how neatly their colours align, with the expectation for sources stretched by expansion to extreme distances. Templates encode possible mixtures of young stars, old stars and dust, and the fitting machinery assigns probabilities, not proclamations. A single colour excess never becomes a certificate. The pattern across several filters must be consistent, and the consistency must survive noise background structure and the subtle tales of the point spread function. Artificial galaxies are injected into the raw frames with known sizes, surface brightnesses and spectra, then recovered by the same algorithms building maps from truth to measurement that expose biases and incompleteness. The output is not the list of brightest curiosities, but a census weighted by the likelihood that each source is what it seems to be. From that census, the next rung demands spectroscopy. The near-infrared spectrograph turns a candidate into a commitment by resolving the spectrum and searching for features whose rest wavelengths are historical facts. The Lyman alpha line is a natural beacon, but the early intergalactic medium can be partially opaque, scattering, or absorbing the very signature observers hope to see. The ladder therefore includes other rails, oxygen and hydrogen recombination lines, at longer wavelengths breaks imprinted by the accumulation of starlight in older populations, and in some cases helium lines that signal hot-low metallicity stars. When the dispersers lay these features at wavelengths shifted by the same factor, confidence hardens into confirmation. Each success also calibrates the prior teaching the photometric selection, how often certain colour patterns truly correspond to a given distance. The process becomes a feedback loop that is not circular, but ascending where confirmed objects refine the templates that find the next set of targets. Programs design their masks and microshutter configurations to include both high-probability candidates and control samples that are likely interlopers, because negative results sharpen the edges of the selection, just as surely as positive ones fill in the centre. There is discipline in chasing lines that do not appear an empty spectrum at the expected place, for a strong feature constrains dust ionization and age, and sometimes rescues a candidate by making an alternative distance implausible. The ladder must also climb across the gap between modest and extreme redshift, where the universe's opacity to short wavelength photons begins to play a decisive role. At intermediate distances, dusty galaxies can imitate the colour break produced by hydrogen absorption, and low-mass dwarfs within the Milky Way can mimic compact red sources. Spectra resolve the confusion. The shape of the continuum slopes the ratio of oxygen lines, and the presence of mid-infrared emission traced by the mid-infrared instrument provide a network of cross-checks that remove the most tempting imposters. Lensing fields add both difficulty and advantage. Magnification can brighten faint high redshift sources into view, but shear and contamination from the lensing cluster complicate extraction. Teams therefore build mass models and convergence maps that are tested against multiple independent reconstructions, and use these to propagate uncertainties in magnification into uncertainties in stellar mass and star formation rate. The ladder is not a straight staircase, but a scaffold with bracing. Every rung is tied to several neighbours. The mathematics of uncertainty travels with the light. photometric redshifts become probability distributions rather than single numbers, and spectroscopic conformations are folded back into those distributions to correct for the winner's curse that arises when bright or compact sources are easier to confirm. The catalogues that emerge from this discipline are not only lists of distances but also atlases of confidence. These atlases are then compared across surveys: the Advanced Deep Extragalactic Survey, the Early Release Science Program on Cosmic Evolution, and the Lens Amplified Survey from Space Overlap in Sky Position and in depth, often enough that many galaxies appear in more than one archive. When the same object earns the same redshift within quoted uncertainties under independent reduction cultures, the ladder gains a rung of communal trust. When a disagreement occurs, the field treats it as a chance to test sensitivity to background subtraction, to spectral extraction windows, or to the treatment of skylines and residuals. In this way, disagreement becomes a tool rather than a fracture. The uppermost rungs at redshifts of 10 and beyond press every component of the ladder into service. At these distances, the Lyman alpha line is often suppressed, so teams search for multiple weaker signatures at longer wavelengths and combine them for the sharpness of the spectral break measured across adjacent filters. The continuum itself, when traced with sufficient signal, can reveal the age of the stellar population through the depth of the Balmer edge, and when that age appears older than the cosmic time available at the measured redshift, a demand for either rapid early growth or for a rethink of assumptions rises from the spectrum. The ladder also benefits from parallel observations. While the near-infrared spectrograph stares at selected targets, the parallel near-infrared imager and slitless spectrograph, or the mid-infrared instrument, collect data on adjacent fields, catching serendipitous spectra or complementary photometry that fill in missing pieces for objects that were too faint or too awkwardly placed for the primary mask. The geometry of these parallel footprints is carefully planned so that repeated visits slowly knit together a more complete coverage without sacrificing depth on the most interesting sources. The strength of the ladder is measured by how it handles the almost right. There are candidates that meet every photometric criterion yet fall short in spectroscopy, not because the distance is wrong, but because the lines are too weak, the background too structured, or the source too diffuse under gentle magnification. For these the community has learned patience without complacency. Stacking in the spectral domain can reveal faint features when many similar galaxies are combined, and joint fits that use both imaging and spectroscopy extract what neither could deliver alone. Observers also design deeper follow-up with narrower slits, cleaner sky windows or alternative grating settings to sidestep the exact obstacles that hindered the first attempt. The ladder, in other words, is willing to rebuild a rung when the wood creaks. Throughout this climb, the thought that perhaps the distances are overestimated lingers like a test that must be repeatedly passed. That is why independent confirmations are handled like currency. When the Atacama Large Millimeter Array detects dust continuum or carbon monophosphide lines at frequencies that match the high redshift solution, skepticism loses another refuge. When gravitational lens models predict multiple images at positions that are actually observed, and the time delay or parity matches expectation, the cosmological stretching factor gains yet another anchor. The more distinct the anchors, the less tempting. The easy excuse that color trickery or algorithmic bias has fooled the eye. By late year 2024 and through year 2025, the accumulation of such confirmations has altered the tone. The field speaks less about whether the ladder reaches these heights, and more about what the view from the top implies. Number counts, size measurements, line ratios, and continuum shapes at confirmed distances collectively argue that early structure grew with surprising efficiency. The redshift ladder has done what ladders are meant to do. It has lifted the discussion from uncertainty about distance to a focused debate about physics. The intrigue deepens, not because the steps are fragile, but because they are firm, and from that firmness, the mismatch with earlier expectations becomes harder to file down. What remains is to climb still higher, to place more rungs where lines are rare and backgrounds difficult, and to keep testing whether each rung holds when a more skeptical climber steps on it. The ladder does not merely support the weight, it invites more of it, and with each ascent the cosmos concedes a little more of the story written into the oldest light. The claim that some galaxies in the first few 100 million years carry more stars, denser cores and brighter hearts than models anticipated begins as an accounting exercise and ends as a challenge to process. Observers take light gathered through the near-infrared and mid-infrared windows where ancient starlight has been stretched and convert it into mass by fitting spectra and colours with physically motivated populations. The ratio of mass to light is allowed to vary with age, metallicity and dust, and the fit that best reproduces the continuum shape, and any detected lines yields a stellar mass along with the range of possibilities implied by uncertainty. When this is done for objects at distances corresponding to redshifts of 10, and beyond a subset appears to carry tens of billions of solar masses in stars, while remaining compact to an extent that their half-light radii span only a few hundred parsecs. The surface densities implied by that pairing of mass and size push against limits where radiation pressure, stellar winds and supernovae are expected to stir and eject gas faster than it can settle. The story becomes sharper when time is folded in. The age of the universe at these distances is measured in only a few 100 million years since the hot beginning, and the ages inferred from features such as the depth of the Balmer edge sometimes claim that a sizable fraction of the stars are not newborn but have already aged by tens or even hundreds of millions of years. If the light is telling the truth, then the main building happened earlier, still compressing the assembly window to a span in which halos must have gathered gas with extraordinary efficiency, turned that gas into stars with a high duty cycle, and retained the products despite the energy those stars release. Dynamics add weight to the inference. Line widths measured in the rest frame optical regime when available allow a rough dynamical mass to be estimated by pairing the internal velocity scale with the measured size. Where these dynamical masses align with or exceed the stellar masses derived from population fits the case for genuine heft strengthens. The combination of compact size and large mass then implies central densities that rival or surpass those of the most intense starburst cores seen much later in cosmic time, yet here they appear without the prolonged history of mergers that normally build such structures. The look of inevitability fades. This is not simply the earliest chapter of a familiar story, but a passage written in a hand that wastes little motion. Models respond by turning every known knob. The rate at which gas cools into halos can be accelerated by allowing cold dense streams from the cosmic web to penetrate hot surroundings and deliver fuel directly to the inner regions, bypassing the shock heating that would slow accumulation. Star formation laws can be made more efficient at high pressure, with greater fractions of gas collapsing into bound clouds that quickly turn into stars. The initial mass function can be tilted toward heavier stars in the earliest metal, poor gas-raising luminosities and altering the pace at which the integrated population reddens. Feedback from young stars can be made more porous carving channels that let energy escape without expelling as much mass, thereby sustaining a high rate of formation in a compact volume. Each change has a signature. A top-heavy distribution of stellar masses alters line ratios the strength of helium features and the production of ionizing photons. Porous feedback leaves imprints in the way gas phases coexist, and in the fraction of ultraviolet light that escapes. Cold streams feeding compact cores should be accompanied by asymmetries and inflow signatures in line profiles when the data are deep enough to find them. Teams go looking for these fingerprints, and sometimes they find hints, but the success remains partial. The abundance of massive compact candidates remains high in more than one field, and while the brightest few may be gently magnified by intervening structure, the magnifications required to resolve the entire discrepancy are usually larger than lens models allow. The next attempt to reconcile observation and theory shifts attention to the way mass is inferred. Dust can redden a young, vigorously forming galaxy until it masquerades as an older, heavier system. If the dust is present in unusual geometries or mixed with stars on scales smaller than the resolution allows, simple screen models can mislead. Mid-infrared measurements that sense warm dust and reprocessed starlight help to break this degeneracy, and in many cases they reduce mass estimates, but they do not erase the population of intense compact objects. Another possibility is that low-level active galactic nuclei contribute continuum and lines that masquerade as starlight. If a central black hole has grown quickly, its light can inflate the stellar mass inferred from a spectrum with mediocre signal. X-ray limits in these fields are often shallow, but line diagnostics and variability tests can flag the most obvious cases. Where an active nucleus is present, the galaxy remains extreme even after the contribution is subtracted. Where it is absent, the mass stays stubborn. The requirement that halos exist to host these galaxies is also demanding. Abundance matching ties the most luminous galaxies to the most massive halos, and the halo mass function at early times falls off steeply at the high end. To house the number of candidates detected, either the conversion of baryons into stars must be unusually efficient, or the halos must be somewhat more numerous than simple growth histories suggest. The first route invites a vision of a universe where the earliest structures are unusually good at turning gas into stars before feedback and heating become dominant. The second route invites modifications to the power spectrum at small scales or to the nature of dark matter, but those invitations come with consequences in other data that must be honoured. The joint constraints from the cosmic microwave background galaxy, clustering and lensing, do not leave much room for radical change without creating friction elsewhere, because the requirements are so tight the community leans on the fine print. Burstiness in star formation can inflate luminosities during a brief phase when a galaxy is caught at a high output relative to its time-averaged rate, and if photometric selection prefers such moments, the census can overrepresent fast risers. Duty cycles can then be used to reconcile number counts with average histories, but this only works if the bursts are intense and common, and if independent measures of age and mass do not insist on long-lived populations. Sizes complicate the picture further. When measured with careful modelling of the point spread function, the smallest sources push the limits of the resolution, and systematic error could bias them low. Teams therefore inject synthetic galaxies with a range of profiles into real images, and recover them with the same methods, measuring how much bias remains as a function of size and brightness. The corrections matter, but even after they are applied, a population with genuinely small radii survives. The implication for internal pressures, star formation, surface densities, and potential wells remain striking. These are systems where gas appears able to condense and stay dense, despite intense feedback, a situation that later galaxies achieve only in short-lived central starbursts or in the immediate aftermath of major mergers. The possibility that central black holes also grow early threads through this narrative. broad or narrow emission features superimposed on some spectra hint that accretion is already underway, and if so, the energy they release could both choke and channel star formation. The coevolution of compact stellar bulges and black holes may therefore begin almost as soon as gravitationally bound structures appear, which would help to explain the surprisingly early appearance of massive quasars observed by other facilities. The galaxy and the engine at its heart would then be partners in rapid construction, each shaping the other in a feedback loop that escalates rather than quenches during the first act. The resolution to the puzzle may not be singular. A slightly heavier initial mass function, somewhat more porous feedback, modest but non-negligible lensing in certain sightlines early, and efficient cold inflows, and a selection that favours systems caught at, or just after a burst could combine, to produce the observed abundance of massive compact sources without any one ingredient being extreme. This blended answer has the virtue of plausibility, but the burden of proof each ingredient must show its fingerprints at a level consistent with independent measurements. The field therefore moves toward targeted tests. Deep spectroscopy aims to isolate age-sensitive features and to separate stellar from non-stellar light with enough fidelity to prune mass estimates. High-resolution follow-up both from space and from interferometers on the ground seeks to map gas kinematics and to detect inflows or outflows that would confirm a particular mode of growth. Lensing reconstructions continue to be refined to remove the last refuge of hidden magnification. Alongside these simulations that include radiative transfer non-uniform feedback and cold stream geometry are run at higher resolution so that compactness and burstiness emerge from physics rather than from parameter choices. Step by step, the thesis that these galaxies are simply too massive too soon becomes a set of quantitative questions about efficiencies, duty cycles, and microphysics. Whether the answers come from familiar processes pushed to their fastest lawful limits, or from gentle adjustments to the rules that govern those processes remains the open edge. For now, the weight of evidence leans toward the former, but the balance is delicate, and the earliest light continues to press its case with a confidence that forces the models to keep up. Spectral whispers carry the weight of ancestry, and in the earliest galaxies those whispers arrive as small changes in slope, as quiet steps between adjacent bands, and as narrow lines that rise above the continuum with the confidence of atomic clocks. The Balmer break carved into a spectrum when the light from many stars accumulates past the energy needed to lift an electron in hydrogen's second level is a modest cliff in the rest frame optical region, and when instruments measure that cliff at wavelengths stretched into the near-infrared, the implication is that a population of stars has already aged enough to pile up a surplus of low mass. Longer-lived members whose combined light makes the break visible. At cosmic times of only a few 100 million years, such a feature suggests not only ongoing formation, but also earlier episodes that have already matured, turning the simple picture of a first-generation lighting up for the first time into a layered account with chapters already turned. Oxygen and hydrogen recombination lines refine the picture. Doubly ionized oxygen and singly ionized oxygen produce strong features in the rest frame optical, and when those features appear with intensities and ratios that demand an ionizing field both hot and hard, the data point toward massive metal. Poor stars that pour out photons energetic enough to carve large ionized regions. Helium lines in particular, the transition that lands at roughly 1,640 angstroms in the rest frame are especially telling, because they require even harder radiation to excite. When that helium line appears narrow and spatially extended, it argues for a stellar origin, for clusters of young, very hot stars whose temperatures tilt toward the upper end of what normal populations supply. when the same line appears broader or accompanied by features that trace very high speeds or dense inner regions. An accreting black hole is implicated, and the story bends toward a compact nucleus turning gravitational energy into light. The chemistry sketched by heavier elements speaks to cycles that would seem to require more time than the clock allows. The presence of oxygen, neon sulfur, and even a hint of iron implies that massive stars have already lived and died to enrich the gas, because those elements are forged in cores and spread by supernovae. If the relative strengths of oxygen to hydrogen lines are moderate while nitrogen remains weak, the metallicity lands low as expected for early times, yet not primordial. The gas has been touched by at least one round of fusion. In a few candidates, line ratios and the faintness of the metal lines together suggest a mixture in which a trace of pristine or nearly pristine material remains, offering the possibility that observers are seeing the glow of a population approaching the long-anticipated first stars that formed without any heavier elements at all. The most evocative hint of such a population is the presence of helium lines stronger than usual and a continuum that slopes upward in the ultraviolet with a starkness that ordinary stars struggle to produce. Yet the interpretation is delicate. Nebular continuum from free-bound and two-photon processes can fill in the spectral regions around the Balmer edge, and the Lyman edge softening or sharpening apparent breaks in ways that can masquerade as ages, when they are instead driven by ionized gas. Intense line emission can also leak into broadband filters, making a galaxy look brighter in a given band for reasons that are not continuum light. To avoid these traps, teams build spectral energy distribution models that include both stellar and nebular components, with self-consistent ionization and metallicity, and they test whether the same parameters that fit the lines also fit the shape of the continuum across many filters. When the fits cohere, the confidence that the break is real and that the lines trace their claimed temperatures and densities grows. Dust adds another layer to the whisper. Very early dust grains born from the ejecta of supernovae or from the winds of the first generations of stars can redden the light and sculpt the continuum. In the mid-infrared, broad features associated with complex organic molecules known as polycyclic aromatic hydrocarbons may appear, but at the lowest metallicities those features weaken, and their absence becomes a statement about chemistry rather than a failure of detection. Observers therefore use the presence or absence of mid-infrared emission together with the slope of the ultraviolet continuum to separate truly old populations from young dusty ones. When the mid-infrared luminosity is low, yet the ultraviolet slope is still moderate rather than extremely blue, the case for a mixed population that includes an older component becomes stronger. In a handful of sources, stacked spectra reveal weak oxygen and sulfur lines, together with a Balmer break creating a composite portrait of a galaxy that has both very recent vigorous star formation and a foundation laid earlier. The timing encoded in the line widths themselves becomes another chronometer. Narrow lines suggest regions dominated by star formation in relatively calm gas, while broader bases or asymmetric wings point toward outflows driven by winds and supernovae. If outflows are already present at such early times, then feedback has had time to carve channels, which in turn affects how ionizing photons escape and how subsequent generations of stars form. The fraction of escaping ionizing photons matters for cosmic reionization, and line ratios sensitive to the hardness of the radiation field and to the density of gas together with the shape of the continuum, just shortward of the Lyman limit, when it can be inferred indirectly begin to constrain that fraction. Galaxies that are compact and intense are natural candidates for high escape fractions, because radiation pressure and winds can clear low opacity paths, and the spectra sometimes echo this with reduced recombination, line-equivalent widths relative to the ultraviolet continuum. Early metal lines also encode yields. The ratio of alpha process elements like oxygen and neon to iron can hint at the relative contributions of core collapse supernovae, which enrich quickly, and thermonuclear supernova, which enrich more slowly. If alpha elements dominate while iron lags, the enrichment clock points to a schedule where massive stars do the early work as theory predicts, yet the measured amounts still demand that several cycles have already occurred. In the most extreme cases, very broad, strong oxygen lines combined with the distinctive continuum could betray the aftermath of pair instability supernovae, which leave no remnant and dump large yields of oxygen into their surroundings. Claims of such signatures are provisional, since the lines are faint and the backgrounds complex, but even the attempt to identify them shows how the spectra have moved the discussion from possibility to measurement. Careful observers worry about every way that a spectrum can lie. Instrumental scattering can carry light from a strong line into neighbouring wavelengths, creating false slopes if not properly modelled. Sky backgrounds change and can imprint structure that looks like a feature. Slit losses and aperture choices can tilt the continuum, as can the inclusion of nearby companions or the soft wings of a foreground star. These risks are not ignored. They are treated as parts of the experiment. Multiple dispersers, repeated visits, alternative extraction windows, and forward modelling that passes physical source profiles through the instrument response reduce the probability that a whisper is only an echo of the apparatus. When an independent team confirms the same subtle break or the same weak helium line in data taken at a different time and reduced with a different code, the doubt that healthy skepticism raises begins to recede. Outside confirmation also comes from other wavelengths. The Atacama Large Millimeter Array, by detecting coal dust or lines of carbon monoxide or singly ionized carbon at frequencies that match the high redshift solution, pins down the distance and affirms the presence or absence of mature dust. The absence of strong dust emission in a galaxy that nevertheless shows a Balmer break leans away from the dust-mimicking age explanation, while the presence of dust in a galaxy with very hot line ratios suggests a scenario in which rapid enrichment has already seeded grains amid intense radiation, a combination that challenges simple timelines. In rare cases, gravitational lensing splits a source into multiple images, and the spectra of those images, when compared, reveal whether the features are intrinsic to the source or artifacts of one particular extraction. The outcome of this attention is that the spectra of early galaxies no longer read as blank placeholders awaiting time. They read as layered documents. The continuum speaks to the blend of ages the breaks fix minimum timescales, the lines frame temperatures, densities, and ionization states, and the elements name the furnaces that have already run. When those furnaces include the production of oxygen and neon in quantities that are modest but non-zero, the simplest conclusion is that the universe did not wait long to loop its first cycles of birth and death. The possibility that a trace of truly primordial light survives in the same systems adds pathos to the scene because it suggests that the universe's first and second acts overlap on stages smaller than a kiloparsec. The intrigue swells for precisely this reason. The elements speak with histories that should barely fit into the available time, and yet the grammar of their lines and the punctuation of their breaks insist that those histories are already written, inviting models to show how such rapid prose can be drafted without breaking the laws that give structure to the tale. Dust appears before the calendar seems willing to allow it, and its quiet glow revealed in the mid-infrared and in the millimeter bands tells a story of fires already burned and ashes already laid. In the earliest galaxies, the continuum from warm grains rises above the starlight like a low hillside against distant mountains, and when teams fit that rise with physical models of emission from silicate and carbonaceous particles, they infer dust masses that require prior generations of stars to have lived and died. Supernovae offer a swift forge condensing grains in cooling ejecta within a few years of the blast, but those same shocks that make the grains can also unmake them, grinding fragile cores into smaller fragments, or into gas. The balance between creation and destruction becomes a central character, and observations suggest that enough grains survive to seed further growth in the interstellar medium, where atoms accrete onto existing surfaces in the quiet eddies between blasts. The pace of that growth must be quick because the universe at these distances is only a few 100 million years old, and the presence of dust substantial enough to dim ultraviolet light and to reprocess it into the infrared implies a cycle of enrichment already well underway. The spectral fingerprints of dust are as telling as its excess light. Extinction curves derived from the slope of the ultraviolet continuum often resemble those in metal, poor nearby galaxies with steeper rises toward short wavelengths, and with the well-known bump near roughly 2,175 angstroms, weak or absent, suggesting a grain population dominated by small silicate particles rather than by the carbonaceous carriers that strengthen the bump. In the mid-infrared, the broad features commonly associated with polycyclic aromatic hydrocarbons are sometimes faint or missing a result consistent with low metallicity and with hard radiation fields that can destroy complex molecules as quickly as they assemble. Where those features do appear, they whisper that carbon chemistry has already taken steps beyond the simplest chains, threading a path from the first ashes toward more elaborate compounds. Measurements of the dust-to-gas ratio when they can be inferred by pairing dust continuum with molecular line traces tell a complementary tale. Ratios rise with metallicity, even at early times as they do locally, but the normalization appears shifted such that for a given metal content the dust fraction can be higher than expected, a sign that grain growth in the interstellar medium may be unusually efficient when densities are high and when turbulent cascades produce many collision opportunities. Against this, the cosmic microwave background raises the floor on dust temperature at high redshift, making cold grains warmer and therefore brighter per unit mass, which in turn lowers the mass required to explain a given flux. Teams therefore correct for the background both as a source of heating and as a source of contrast loss, because the same background that warms the grains also fills the beam with radiation that can hide faint emission. After those corrections, many sources still demand substantial dust masses, and the conclusion that early enrichment is real survives. The geometry of dust within these compact galaxies deepens the question. If grains are mixed with stars on scales smaller than the angular resolution, then simple screen models underestimate the fraction of light absorbed, and photometric fits can misinterpret reddening as age. The addition of mid-infrared points from the Space Observatory and from facilities on the ground reduces this degeneracy, because the energy absorbed must reappear as thermal emission, and when the energy budget closes without invoking heavy dust, the case for older stars weakens, while when it refuses to close dust becomes the missing term. In many systems, the budget insists on dust. The infrared excess to ultraviolet slope relation, a tool that ties the redness of a spectrum to the amount of reprocessing lands in territories that require attenuation beyond what a transparent young population would experience, and yet the mid-infrared luminosities are not always immense, suggesting that the dust is present, but not dominant a veil rather than a wall. Grain sizes and compositions issue their own demands on the physics. Grains formed in supernova ejecta can be relatively large if they avoid shattering, which makes them resilient to destruction, and efficient at absorbing and emitting, while grains grown in the interstellar medium can begin small and grow by accretion, changing the opacity curve and the temperature distribution. The observed steepness of ultraviolet extinction and the weakness of aromatic features together favour a picture in which supernovae seed the medium with silicate-rich cores that then fatten in dense pockets, while carbonaceous complexity lags behind. If that is true, then the dust-to-metal ratio should evolve rapidly, and early galaxies should show increasing infrared output as successive cycles loop through. Line diagnostics confirm that cycles are indeed looping. Oxygen and neon abundances measured from nebular lines rise above primordial values, while nitrogen remains modest, a chronology that fits the rapid enrichment by massive stars, and that leaves just enough time for dust to condense and for grains to thicken. In a few extreme sources, very broad oxygen lines and a striking continuum shape hint at the aftermath of pair instability supernovae, which could dump large yields of oxygen and fuel a burst of dust formation. The claims are tentative, but they sit comfortably within the broader narrative that heavy element production, dust formation, and selective survival are already shaping the light. Gravitational lensing occasionally lifts the veil further by magnifying the smallest, dustiest regions into view, revealing clumpy structures in which star formation and dust coexist in knots, where radiation pressure pushes outward and turbulence folds back in. Those knots likely harbour the conditions for rapid grain growth, high extinction, and efficient reprocessing, and they may explain why some compact galaxies radiate with mid-infrared colours that imply warm dust despite modest total mass. The presence of dust at these early times does more than complicate photometry. It participates in the thermodynamics of the gas. Grains provide surfaces for molecule formation, including the creation of molecular hydrogen, which cools gas and accelerates collapse, thereby promoting further star formation. At the same time, dust absorbs ionizing photons and hard ultraviolet light, which can either reduce the escape fraction needed to reionize the intergalactic medium, or paradoxically open low opacity channels by coupling radiation pressure more strongly to dense clumps and clearing sightlines. Spectra that show high ionization parameters together with signatures of outflow suggest that both processes operate with dust acting as both catalyst and gatekeeper, shifting the balance from place to place and from moment to moment. The community does not accept dust without stress testing the scales. Modified blackbody fits assume temperatures and emissivities that can bias masses high or low, so teams use multiple wavelengths to constrain the temperature distribution, and they compare single temperature models with mixtures that approximate the range from cool diffuse clouds to hot star-forming regions. They simulate observational pipelines with artificial sources that include the cosmic microwave background and instrumental noise measuring how often faint dust emission is lost or exaggerated. They cross-check with independent facilities that observe at different frequencies and resolution-seeking agreement that does not depend on any one instrument's idiosyncrasies. As these checks accumulate, the assertion that early dust is real crystallizes into a demand on theory. Models that begin with metal-free gas and proceed through the first bursts of star formation must not only produce the right number of luminous compact galaxies, they must also deposit enough heavy elements and enough surviving grains to match the observed infrared glow without overproducing the ultraviolet attenuation that would erase the detections in the first place. That demand tightens the allowed combinations of star formation efficiency, feedback, porosity, and initial mass function, and it leans towards scenarios in which the earliest supernovae are prolific dust factories and in which interstellar growth is quick. the irony that the ashes may be necessary for the flames is not lost. In these galaxies, dust seems to help stars form even as it hides their light, and by doing so it writes itself into the schedule as both witness and accomplice. The intrigue gathers precisely because the dust appears not later as a footnote, but sooner as a premise laid down before time had much chance to pass, turning what might have been a clean first dawn into a scene already veiled by the smoke of prior fires, and inviting models to show how the sky learned to make embers almost as soon as it learned to make stars. Background glows and shadows stretch across the sky like the finest grain in a photograph, and as instruments peel away bright stars and nearby galaxies, what remains is a low persistent shimmer that carries the sum of many unresolved sources. The cosmic infrared background is the reddish fog built from the light of galaxies and dust, warmed by stars across all epochs, and when observers measure its fluctuations after masking every detected source down to the threshold of deep fields, they find a pattern that is small but stubborn, stronger at certain angular scales than simple extrapolations from known populations would predict. This excess is not enormous. It is a thread pulled slightly tauter than expected, yet it persists across instruments and analysis choices, and thereby it becomes a clue. Cross-correlations with catalogues from deep imaging show that part of this grain is indeed tied to very faint galaxies just below detection, but a residual component often remains one that clusters more strongly than a naive halo model tuned to later times would suggest. Several ideas compete to own this residue. Intra-halo light produced by stars that have been stripped from their parent galaxies and wander within the gravity wells of groups and clusters contributes an extended glow that can be difficult to subtract, and that would naturally cluster with halos without requiring an excess of early galaxies. Yet the angular scales, where the signal is strongest, sometimes favour more distant, less massive hosts. Early star formation, especially in compact low metallicity systems with hard spectra, could radiate efficiently in the near-infrared once redshifted, leaving a fingerprint in the background that complements resolved counts. The truth may mix both, but the act of unmixing becomes the test. Observers stack infrared images on the positions of galaxies detected at other wavelengths and measure the average excess, carefully propagating masks to avoid bias from the wings of brighter objects. They construct maps from which all known galaxies and stars have been subtracted, and then correlate those maps with weak lensing convergence fields built from background galaxy shapes. Because if the residual infrared light truly traces structure, it should track the distribution of mass. The correlations often appear, and their amplitude sets a scale for how much of the glow belongs to structures at given distances. In parallel, the cosmic microwave background provides a baseline canvas that is astonishingly smooth with tiny fluctuations that act as a ruler for the distribution of matter at early times. When lensing distortions in the microwave background are compared with infrared background maps, the degree of alignment informs how much of the infrared glow arises from high redshift sources versus relatively nearby dust. Where the alignment is imperfect by small but repeatable amounts. The inference is that a piece of the infrared grain may come from epochs or environments whose clustering differs subtly from the more familiar landscape that shapes the microwave background. Shadows in the background are as informative as glows. The shadows cast by the Lyman alpha forest in the spectra of bright background sources reveal the distribution of neutral hydrogen, and while that technique is not directly a map of the infrared or microwave backgrounds, it provides a contemporaneous account of ionization that must be consistent with whatever population claims ownership of the infrared excess. If compact efficient galaxies at very high redshift contribute significantly, they should also leave signatures in rionization histories derived from the scattering optical depth of the microwave background and from the temperature of the intergalactic medium as probed by absorption. Current measurements allow such contributions but constrain them. The allowed window remains open yet narrow, and the background glow must pass through it. Subtle lensing imprints introduce another class of shadows. Weak lensing by large-scale structure shears the shapes of background galaxies and slightly magnifies or demagnifies their fluxes. When applied to deep maps, the statistical pattern of the shear field can be inverted into a convergence map, essentially a projection of mass. If the infrared background fluctuations are truly sourced by a sea of faint early galaxies, then after removing the known lower redshift populations, the residuals should correlate with convergence in a way that rises towards small angular scales and high redshift kernels. Early analyses often hint at this, but the agreement is never perfect. Small misalignments and amplitude mismatches linger. Some of that mismatch may be the fault of dust in our own galaxy, whose filaments, though faint at high galactic latitude, can scatter and emit at levels that become consequential once most of the extragalactic light has been subtracted. Teams fight this by correlating with maps of neutral hydrogen in our galaxy, and by using multi-frequency data to model and subtract the spectral signatures of dust. The residual after such subtraction still tends to carry a clustering signal that is difficult to explain entirely, with local dust keeping the door open for a distant origin. Another shadow is cast by the kinetic Sunyaev-Zeldovich effect, where the motion of ionized gas imprints tiny temperature shifts on the cosmic microwave background via scattering. The magnitude and angular pattern of this effect constrain the patchiness and timing of ionization, and these constraints must agree with any scenario that attributes a large piece of the infrared background to very early efficient star formation, as estimates of the kinetic Sunyaev-Zeldovich power improve the window for extremely extended or extremely early ionization narrows. The infrared background excess, if it does arise in part from high redshift galaxies, must therefore be produced without pushing ionization histories outside those limits, implying either that the responsible galaxies are efficient in producing near-infrared light per ionizing photon, or that they sit in environments where many ionizing photons are trapped locally and reprocessed. The play between glows and shadows thus becomes an accounting of energy and timing. On top of this, strong gravitational lensing provides clocks that test the expansion history, and thus the mapping from redshift to time. When time delays between multiple images of background sources are measured and used to infer the Hubble expansion rate, the resulting value sets the scale for cosmic ages at a given redshift. If those delays point consistently to an expansion rate that shortens the age available at early times, the tension with bright compact sources would sharpen. If they lengthen the age, the tension would ease. Current reconstructions distribute their weight between these outcomes, with systematic uncertainties in lens mass models and in line-of-sight structure still under investigation. Small differences between infrared background clustering and microwave background lensing could in principle arise if early structure carries different bias than later structure, or if light from diffuse sources such as intra-halo stars fills large scales in a way that resolved galaxies do not. Simulations attempt to reproduce these effects by populating halos with both galaxy light and diffuse stellar components, evolving dust and tracking radiative transfer through patchy ionization. They recover some features but not all, and the places where they fail most stubbornly often sit exactly on the angular scales where observations report the most persistent residuals. This is where the intrigue widens the canvas. At the larger scales is not wildly discordant, but it is in a statistical sense misregistered by enough to resist easy comfort. The reaction across the field is sober rather than sensational. Analysts continue to refine masks to vary foreground models to repeat cross-correlations on independent data and to seek systematics that might quietly drive the residuals. At the same time, they design observations that directly test the hypotheses. Wider yet still, deep fields can better separate clustering from shot noise and trace the rise and fall of the infrared excess with environment. Joint analyses that treat the infrared background, weak lensing and microwave background lensing within a single framework can pull consistent history from the overlapping kernels of sensitivity. The goal is not to elevate small disagreements into dramatic claims, but to ask whether the early universe left a faint extra glow in the background that points toward more abundant or more efficient structures than a conservative script would have scheduled. Against the smooth certainty of the microwave background, that possibility reads as a quiet offbeat, not enough to break the rhythm enough to change the feel. If confirmed, it would mean that the first builders left not only bright knots in deep images, but also a collective signature woven into the sky's fabric, a pattern of glows and shadows that anchors the story of early assembly to the widest frame available. Echoes that seem to speak from before the overt opening scene invite a return to the stories told about the earliest moments when space itself was stretched smooth and cold. Patches were amplified into the seeds of structure. The inflationary idea explains why the sky looks uniform on scales larger than communication should allow, and why the faint irregularities in the cosmic microwave background form a pattern that nearly matches the simplest predictions of quantum fluctuations stretched to astronomical size. Yet the count and compactness of early galaxies, the hints of excess in the cosmic infrared background, and the small misregistrations between background maps and lensing kernels coax theorists to look again at the prelude. If the light from the first builders looks older than the schedule set by a single featureless inflationary episode, perhaps the opening act had more structure than a smooth single line. One path is to alter the way that fluctuations were laid down. The simplest inflationary models predict a nearly scale, free, slightly red spectrum of density variations, with modest departures from exact scale invariance and tiny non-Gaussian signatures. To tilt the balance toward early formation, without wrecking the wonderful agreement on large scales, models can introduce brief features or secondary fields that raise power at small scales while leaving the large scales almost untouched. A step in the inflaton potential, a bend where the field briefly slows or speeds, or a resonance when the field couples to another light field, can imprint a bump in power that would later collapse into unusually early, unusually dense halos. Such features would live at scales too small for the cosmic microwave background to measure directly, yet large enough to influence the assembly of the first galaxies. The consequences include a higher rate of early star formation and more efficient seeding of compact structures, both of which mirror the hints now seen. A second path is to diversify who does the seeding. In curvaton scenarios, a spectator field that is almost passive during inflation later hands its perturbations to the plasma, after the primary inflaton has decayed. If the curvaton carries different spectrum or generates mild non-Gaussian correlations, it can change how small scales grow without upsetting the statistics already pinned down on the larger scales. A dark sector with feeble couplings could play a similar role with fluctuations that do not immediately affect photons or baryons, but that guide the formation of early halos, thereby raising the odds that some lines of sight encounter compact luminous structures sooner than a single field story would arrange. The thermal history during reheating also matters. If the process by which the inflaton decayed into ordinary particles produced a bath that was cooler than often assumed, the mapping between horizon crossing scales and present-day wavelengths shifts, and the growth of small-scale structure can be altered in subtle ways. A cooler start need not delay all structure, if there are islands in the spectrum where power is higher. Instead, it can reshuffle the schedule so that certain scales become privileged sites for early collapse. Observables that test these ideas live in several corners. Non-Gaussianity, even at levels below the sensitivity of current cosmic microwave background maps, can alter halo abundances by raising the probability of rare peaks. The shape of the halo mass function at the earliest times as inferred from number counts of compact galaxies or from intensity mapping of aggregate emission becomes a ruler for such effects. If the earliest halos are more numerous than expected at a given mass, and if that excess fades by later times, the signal whispers a memory trace from inflation. The same trace may appear as a surplus of small cold clouds in the intergalactic medium, or as a particular pattern in the clustering of faint sources that quoted simple bias models fail to capture. Primordial gravitational waves, the long-sought curling pattern in the polarization of the microwave background, address a different span of the script. A large signal would point toward energy scales where tides in the geometry were strong during inflation. A very small or absent signal would favor gentler slopes. Either outcome taken together with small-scale structure constrains the menu of viable potentials and couplings. If early structure requires a boost on short scales while gravitational waves demand low energy, or many gentle fields, the space for a single elegant model narrows, which encourages consideration of richer dynamics that were once set aside as baroque. Cosmic strings and other relics of symmetry breaking offer another way to paint fine grain into the sky. If inflation ended with a phase transition that left behind thin, long defects, their gravitational fields would lens background radiation and leave line discontinuities or small distortions in maps. Surveys have constrained such relics, but not so tightly as to preclude contributions at a level that might add low-level power at specific scales. Similarly, primordial black holes formed from enhanced small-scale fluctuations could seed early star formation, both by serving as dense centers and by injecting energy into their surroundings. The permissible abundance is limited by many observations, yet a small fraction is still allowed, and even a small fraction at the right mass scale could modulate early assembly in ways that resemble what is seen. Beyond the inflationary script, pre-inflation relics or modified initial states have been proposed to account for faint quirks. If inflation lasted just barely longer than needed, the largest observable scales might retain memory of a prior phase, but even modest deviations could bleed into medium scales through couplings leaving soft features that, when evolved, change the distribution of early halos. Trans-Planckian ideas that alter the vacuum at the start, or bouncing scenarios that feed initial conditions into the inflating phase, have been explored with caution as they sit close to the edge of what can be discussed with confidence, yet they serve as reminders that the beginning of the beginning is not directly observed but reconstructed from later imprints. The discipline demands that such ideas earn their place by predicting not only more early galaxies, but also patterns in line ratios, sizes, and background correlations that match what the data actually show. The best versions do not simply add power, they shape it in ways that can be checked. For example, a bump in small-scale power should produce not only more halos, but also more lensing by tiny structures, which would subtly change the magnification distribution of background sources and the small-scale shear field. It should also leave a signature in the distribution of Lyman alpha emitters and in the clustering of the faintest galaxies that future surveys can measure. Meanwhile, the interplay with the nature of dark matter cannot be ignored. Warm dark matter would suppress small-scale power and thus deepen the puzzle. Cold dark matter allows small halos, but must be partnered with baryonic physics that in turn chooses whether those halos light up early or remain dark. If inflationary echoes amplify small scales, they may rescue early assembly, even in the presence of moderate suppression by a slightly warm dark matter candidate, but they must then thread the needle between abundance and emptiness. The reason the community revisits inflation now is not to discard a framework that has earned trust, but to ask whether the framework has room for a little more preface. The approach remains experimental at heart. Teams search for running of the spectral index beyond what the simplest fits allow, for hints of oscillatory features in power spectra that would betray resonances for scale, dependent non-Gaussianity that would point to additional fields, and for distortions in the cosmic microwave background frequency spectrum that reveal episodes of energy release in the very early universe. Crosstalk with large-scale structure deepens the reach as intensity mapping, weak lensing, and galaxy clustering at higher redshift join with a background to triangulate the fingerprints of the prelude. In the end, the attraction of these echoes is not that they promise drama, but that they offer a gentle adjustment to the script that could make the early brightness and compactness of galaxies feel less rushed. A small rise in small-scale power, a spectator field that adds texture without upsetting the broad strokes, or a reheating story that nudges the mapping between scale and time could together tilt the balance toward earlier builders. If such nudges also explain the faint residuals in background maps and the stubborn compactness that photometry and spectroscopy insist upon, then the prelude gains plausibility. Until then, theories of inflation and of its immediate aftermath remain open to revision, ready to absorb what the earliest lighters whispered, and ready if necessary to disclose that the overture was layered with hidden movements that set the rhythm long before the hot beginning announced the theme. Gravitational lenses turn mass into geometry and geometry into clocks, and in the earliest chapters of structure formation, these clocks test the schedule that maps redshift to time. When a foreground galaxy or cluster deflects the light from a more distant source, multiple images appear, each traveling a path with a different length through a different potential well. Variations in the source's brightness, whether intrinsic flickers from an active nucleus or the explosive rise and fall of a supernova, reach those images at different moments, and the separations between those moments are time delays that depend on the shape of the lensing potential and on the overall scale of the universe's expansion. The arrival time surface, a landscape drawn by Fermat's principle, encodes both the geometric path differences and the gravitational slowing of light near mass, and its curvature translates variations in the source into a set of lags that can be measured and compared to predictions. In principle, this turns each strongly lensed transient into a chronometer, and when the lens mass distribution is modelled with care, the measured delays invert into a value for the Hubble constant and into cross-checks on the way matter is distributed across the line of sight. In practice, the chronometry is delicate. The mass sheet degeneracy allows a family of lens models to produce identical image positions and shapes, while shifting the inferred time delays by a global factor, and that degeneracy can be broken only by independent information about the absolute mass scale, by the stellar kinematics of the lens, or by knowledge of the source size and structure that constrains how magnification should behave. Line-of-sight structures add further complication galaxies and groups that do not sit exactly in the lens plane, but still contribute convergence and shear, can bias the delays unless their presence is mapped and folded into the model. Analysts therefore combine high-resolution imaging of the arc spectroscopy of both lens and source-wide field redshift surveys along the sightline, and dynamical measurements of the lens stars to tie the model to the sky. With this scaffolding, lenses become clocks that tick in units set by cosmology. When the delays from several well-studied systems are combined, the expansion rate inferred sometimes favours a value for the Hubble constant that differs from the value inferred from the earliest background radiation, and although uncertainties still allow reconciliation, the tension is not trivial. If the lens clocks consistently run a little fast or a little slow compared to the background's calendar, the earlier structures gain or lose time strengthening or easing the pressure created by bright compact galaxies at high redshift. Some of the difference may flow from systematics in mass models. Power law profiles that fit arcs neatly may hide subtle deviations in the central slope, and those deviations matter because they shape the arrival time surface. Composite models that include both a stellar component with an effective radius and a dark halo with a flexible inner profile can match the data with more physical realism, but they require priors that must be justified by independent observations. The stellar velocity dispersion of the lens measured by absorption line widths in spectra ties the inner mass to dynamics, and thereby constrains the profile, yet anisotropy in stellar orbits and gradients in mass to light ratio can leak into the inference if left unmodelled. The community responds by building hierarchical analyses that treat these uncertainties as part of the fit, and by selecting lenses where the host galaxy of a lensed active nucleus is visible, and provides extended structure that anchors the reconstruction. Transients add a further advantage. Lensed supernovae serve as nearly standardizable candles, whose intrinsic luminosities can be inferred from their light curves and colors, so that absolute magnifications become measurable. Absolute magnification breaks the mass sheet degeneracy in a way unavailable to active nuclei, and the resulting delays become more direct probes of cosmology. The Space Observatory's sharper view contributes two critical improvements. First, it resolves arcs and host galaxies into substructures that carry information, rich constraints on the lens potential, allowing pixel-level lens modeling that treats the source as unknown and recovers both source and lens together. Second, it detects fainter, more numerous lensed galaxies and occasionally discovers multiply image transients, early enabling full light curve sampling across images. In fields where clusters lens the background into grand arcs, the same geometry that magnifies faint high redshift galaxies also times their flickers, turning the cluster into a clock tower whose faces point in different directions but strike the same hour with offsets determined by the mass map. The timing then checks the cluster model that observers already use to estimate magnifications for the compact early sources central to the larger puzzle. If the clock and the magnification map agree, the confidence in the inferred brightness and hence in the mass and size of those sources grows. If they disagree, the model demands repair. Micro-lensing by stars in the lensing galaxy complicates the timepiece by superimposing small time-dependent magnifications on the macro images, changing brightness without changing arrival times. For active nuclei with compact emitting regions, micro-lensing can be strong and can bias delays measured by correlating light curves. Observers handle this by modelling microlensing as an additional stochastic process, by focusing on features less sensitive to microlensing such as broadline regions, whose sizes are larger, and by exploiting supernova light curves where the photosphere expands, changing the microlensing signature in a predictable way that can be fitted jointly with the macro delay. The path forward multiplies the clocks. Surveys that monitor wide areas catch dozens of lensed active nuclei and a growing handful of lensed supernovae each year. For each, the combination of deep imaging, precise time series photometry lens, and source spectroscopy and line of sight mapping builds a case that is both specific and cumulative. Individually, a system yields a value for the expansion rate and serves as a test of lens modelling. Collectively, the ensemble averages down idiosyncrasies and pushes systematics to the surface. The ideal outcome is not only a sharper measure of the scale of the universe, but a model for each lens that is trustworthy enough to support claims about magnification in the same field, thereby calibrating the role of lensing in inflating the numbers and brightnesses of early galaxies. Even null results inform the story. If time delays in cluster lenses confirm mass maps that predict only modest magnifications for most lines of sight, then the abundance of bright compact sources cannot be explained away by hidden, widespread strong lensing. If, on the other hand, a tail of lines of sight carries higher than expected magnification, because substructure or anisotropic mass distributions are more common than models assume, some fraction of the early excess may be attributed to nature's boost. The clocks will decide. As more delays are measured, and as models of individual systems are tied to stellar kinematics and to independent weak lensing, the error bars on the expansion rate sharpen, and the field learns whether the cosmic calendar needs revision. At the same time, each well-modelled lens becomes a laboratory for the small-scale distribution of dark matter, because the way images split and the way delays distribute depend on subhalos and on the smoothness of the potential. Those inferences circle back to the origin story of early compact galaxies, since the ease with which gas collects and cools depends on the same small-scale power that lenses test. In this way, gravitational lenses act as both magnifying glasses and timekeepers, and by counting beats as well as photons, they coil intrigue through warped paths that test whether the universe has scheduled its earliest acts exactly as long assumed, or whether in the fine print of mass and time the script has been counting a little fast or a little slow. Simulations under strain reveal where understanding bends, because they take the rules we believe describe gas gravity radiation and star formation, then let those rules run forward to see what universe they make. The leading hydrodynamic suites evolve billions of particles or fluid elements across large volumes, while zooming into regions where galaxies assemble, and they include recipes for how cold clouds collapse, how stars ignite, how young stars and supernovae inject energy and momentum, how black holes sink, accrete, and drive winds, and how radiation heats, ionizes, and exerts pressure. When confronted with the counts of compact bright galaxies at extreme redshift, and with spectra that hint at older populations and surprisingly early dust, these virtual universes scramble. The first response is to raise the efficiency of turning gas into stars at high pressures, because the earliest halos are small and dense, and a rule that links freefall time to star formation rate can be tuned to make such environments prolific. The second response is to let feedback ventilate without expelling too much mass, by opening chimneys in the interstellar medium through which energy can escape while leaving dense clumps intact. The third response is to allow central black holes to start earlier and to stir less so that they coexist with star formation, rather than shutting it down. Each of these maneuvers increases the number of luminous early systems, but none alone fully solves the joint constraints of abundance, compactness line ratios, and dust. When efficiency is raised too far, later galaxies become too massive and too quenched compared to observations at intermediate redshift. When feedback becomes too porous, metal enrichment and outflow signatures fall short of measured values, and the circumgalactic medium becomes too quiet. When black hole growth is gentle, the predicted number of bright quasars at early times drops below what has been seen by surveys that do not depend on the Space Observatory. The models can split the difference, but the seams show. The structure of compactness is even harder to conjure. To match measured half-light radii of only a few hundred parsecs, simulated galaxies must funnel gas to the center with extraordinary stability avoiding the angular momentum barriers and gravitational torques that normally spread growth over kiloparsecs. Cold streams flowing along filaments can feed central regions fast if the circumgalactic medium remains cool, and if shocks are weak or absent, but those same conditions must coexist with feedback that is vigorous enough to produce the outflows and ionization parameters suggested by spectra. When the mesh is refined and radiative transfer is included, the interstellar medium becomes clumpy, and time-variable star formation becomes bursty and compact phases do appear, yet their duty cycles are short. If photometric selection favours those moments, number counts can look high for a while, but the derived ages and the presence of dust demand that the bursts are not only frequent, but also embedded within a history that has already layered several generations. The models then add a variable initial mass function heavier at the top in low metallicity gas to raise luminosities per unit mass and to accelerate enrichment. This helps with line ratios and with ionizing photon budgets, and it seeds dust quickly, but it also threatens to overproduce metals and to redden spectra by mid-infrared epochs, unless the top-heavy phase shuts off soon and everywhere. If it shuts off soon, the window for explaining the earliest Balmer breaks narrows again. In this trade space, every patch that fixes one seam opens another. Lensing is treated with care by forward modelling synthetic skies. Simulated galaxies are passed through instrument responses placed behind mass distributions, drawn from the same volumes and measured using the same pipelines as the data, so that magnification, blending, and surface brightness selection effects are captured. The conclusion from these exercises is sobering lensing raises the count of high redshift detections and shrinks apparent sizes for a tail of objects, but it does not easily generate a population as abundant and uniformly compact as the data suggest, unless the underlying galaxies are already small and bright. This returns the burden to baryonic physics. Radiation pressure on dust, when coupled into gas on subgrid scales, can confine star formation to dense pockets, while clearing sightlines that make compact sources appear even more concentrated. Magnetic fields, often neglected or simplified, can provide additional support or channel flows that alter how quickly gas reaches the center. Cosmic rays whose pressure gradients push against gravity and which can escape along field lines change the balance between confinement and venting. When these ingredients are added, sometimes together, compact intense phases become more common and outflows more structured, but the models then struggle to keep the circumgalactic medium in the thermal and ionization states, inferred from absorption studies at later times. The answer may not be a single missing ingredient, but improved choreography among many. Resolution remains a stern arbiter. The scales where star clusters form, where supernova remnants cool, and where radiation couples to dust, are far below the cell sizes of cosmological boxes and subgrid prescriptions, must stand in for the actual physics. When resolution is pushed and subgrid models are calibrated not only to the stellar mass to halo mass relation at later times, but also to observables from local starburst cores, the simulated early galaxies tighten and their duty cycles lengthen. However, the required calibration can feel uncomfortably specific, eroding the sense that the simulation is predicting rather than accommodating. To test whether the accommodation hides circularity groups now publish blind predictions for statistics that were not used to tune the models, including the joint distribution of size and luminosity at extreme redshift, the equivalent width distributions of oxygen lines, and the fraction of galaxies that show mid-infrared excess consistent with dust. Early rounds of this experiment reveal partial success. Simulations can reproduce the slope of the size-luminosity relation, but miss the normalization. They can match the abundance of moderate equivalent width oxygen emitters, but fall short at the most extreme end. They produce dust earlier than older generations of codes, yet not quite early enough to explain the infrared excess in the faintest highest redshift bins. The places where the predictions fall short become maps for where the physics needs reinforcement. Parallel to these efforts, semi-analytical models which treat halo growth with precision and layer baryonic recipes on top explore vast parameter spaces that brute force hydrodynamics cannot. These models show that a blend of modestly heavier initial mass functions slightly higher, star formation efficiencies at high pressures, and feedback that allows gas to cycle through galaxies rather than escape permanently can reproduce many counts without violating later constraints, but they struggle to make the smallest radii without invoking dissipative processes that are difficult to justify in the absence of strong torques or centralized mass concentrations. The link to black holes becomes central again. If seed black holes form earlier or in larger numbers than commonly assumed, their gravitational influence can deepen potential wells, and their radiation can both compress and stir gas. Observing programs that search for faint active nuclei in the same compact galaxies aim to test this, and simulations that plant seeds tied to dense low metallicity clouds find that central growth can begin early without immediately quenching star formation. The coevolution then looks less like a competition and more like a duet, and the compactness emerges more readily. Even within this duet, the broader canvas constrains freedom. The same simulations must also reproduce the number of bright quasars by the time the universe is 1 billion years old, the thermal history implied by the intergalactic medium, the statistics of damped absorption systems, and the wide field clustering of massive galaxies at intermediate redshift. The more boxes a model must check, the fewer places it can hide unphysical tuning. That constraint is healthy. It drives a progression from ad hoc patches toward physically motivated mechanisms that leave fingerprints across many observables. As this progression continues, the community has shifted from asking whether the simulations can match the brightest outliers to asking whether they can match the median properties of the confirmed population across fields and programs. The answer is advancing from no toward almost, and that almost is precisely where intrigue persists. For every improvement, a diagnostic rises to challenge it. Faster early star formation must produce older stars which must sharpen brakes without overproducing mid-infrared light. More porous feedback must leave imprints in line ratios and in the escape fraction of ionizing photons that can be tested by stacking. Earlier black hole growth must leave narrow and broad features in spectra and subtle variability signatures that careful time series can reveal. Dust that grows quickly must shift ultraviolet slopes and infrared colors in ways that can be checked with additional bands. In the coming cycles, simulators and observers are converging on targeted tests designed together. Synthetic skies will be built to mirror specific survey footprints with identical noise point spread functions and selection criteria so that differences cannot be blamed on methodology. In this closing of the loop, the field expects either to bring the virtual universes into comfortable alignment with the earliest light using familiar physics, pushed to lawful limits, or to find that a small but persistent gap remains, pointing not to a mistake in technique, but to a rule that needs amendment. Until that verdict arrives, simulations under strain remain the most honest mirrors of our current understanding, reflecting not only what we think we know, but also where the seam between known and unknown is tightest, and reminding everyone that every patch that fixes one seam tends to open another, which is less a failure than a map for where to look next. Cyclic horizons pull the beginning into a loop and ask whether the cosmos reheats and resets, rather than starting from a singular point and in that loop they offer new ways to seed structures that look older than a single opening would allow. In ekpyrotic models, the universe does not begin with a burst of accelerated expansion, but with a slow, ultra-stiff contraction that smooths and flattens space before a bounce into expansion, so that what inflation provides by stretching ekpyrosis provides by crushing irregularities under an equation of state far greater than 1. During this slow contraction, quantum fluctuations of fields other than the scale factor can generate nearly scale invariant curvature perturbations through entropic conversion, laying down seeds that later become galaxies. Because contraction lasts as long as needed, there is room in the script for small structures to gain a head start without asking the expanding phase to rush. The bounce itself demands physics beyond a simple fluid, since ordinary matter respects energy conditions that forbid reversal. Proposals range from higher derivative operators arranged to avoid ghosts, to couplings that transiently violate the null energy condition in a controlled way to loop quantum gravity corrections that discretize geometry, and produce a deterministic bounce to brain collisions in higher dimensional pictures, where the visible universe sits on a membrane that periodically meets a partner. Each mechanism carries a fingerprint. Ekpyrotic contraction typically suppresses primordial gravitational waves to unobservably small levels, a prediction opposite to many simple inflationary potentials, so a future detection of a strong tensor background would weigh against such cycles, while a persistent absence leaves the door open. Non-Gaussian signatures also differ often, favoring shapes and amplitudes that can be tested as measurements sharpen. Conformal cyclic cosmology goes further by erasing the distinction between a cold, diluted far future and a hot beginning through a rescaling that removes mass scales. In this telling, the remote future of one eon maps conformally to the Big Bang of the next, and very long wavelength structures, or even the integrated effect of black hole evaporation, translate into subtle imprints in the microwave background of the new aeon. Claims of concentric circles with unusually low variance or of specific alignments have been debated, but the deeper point remains that an earlier aeon could feed a gentle memory into the next, without breaking the success of standard physics once the new expansion begins. Emergent scenarios hold the scale factor near a constant for a long quasi-static phase, before a slow roll into acceleration, or a phase transition into hot expansion, and during that park time thermal or quantum fluctuations can generate perturbations with different spectral tilts from ordinary inflation, sometimes favoring slightly blue small-scale power that would help early collapse without upsetting large-scale order. String gas cosmology provides a concrete version with thermal fluctuations of a gas of fundamental strings near a maximal temperature, creating nearly scale invariant spectra and producing distinctive running and correlations between scalar and tensor modes. Because the maximal temperature limits energy to a plateau rather than a blow up the production of small-scale structure, can be gently enhanced while tensors remain small. Each of these prehistories offers knobs that can move power towards scales that form the first galaxies, and because the mechanisms differ from simple single-field inflation, they can also alter the timing of reheating, the thermal history of the plasma, and the early ionization fraction, in ways that ripple forward into the epochs now under scrutiny. To be viable, any cycle must face the problem of entropy growth that Tolman posed a century ago. Each pass-through, expansion, spreads heat and increases disorder, so returning to a similar state requires dilution or disposal. Proposals tuck entropy into black holes that later evaporate, slip it into extra dimensions during interbrain separation, or use the slow contraction to concentrate and then excise it through horizons, but these escapes must be modelled and their byproducts counted. Nucleosynthesis, which is a stern accountant, allows only narrow variations in the early expansion rate and composition, so a bounce or a long loiter must prearrange itself so that by the time light elements form, the rules match those that build the observed abundances. Likewise, baryogenesis requires time and a departure from equilibrium, and any cycle must provide a fresher symmetry, or preserve one without washing it out. These constraints do not block cyclical or emergent schemes, but they turn them from poetic invitations into quantitative systems that must thread needles with care. Where they succeed, they can deliver precisely what the crowded early sky seems to want: extra small-scale structure, or slightly altered growth rates, or older-looking stellar populations, assembled from material that already cycled once. In ekpyrotic models, for example, the entropic mechanism can generate a slightly blue spectrum on small scales, lifting the number of low-mass halos at early times. When those halos merge or accrete cold flows, compact efficient star formation can follow without requiring the expanding phase to race. In conformal cyclic cosmology, vestiges from the previous aeon could appear as mild distortions in the tail of the temperature anisotropy spectrum, or as features in polarization that correlate across multipoles in unusual ways. And if such vestiges bias initial conditions in favor of certain overdensities, they could tilt the odds toward early assembly along specific lines of sight, producing mild anisotropy in the abundance of extreme sources that future-wide surveys might test. In emergent scenarios, a long preparatory phase allows chemical or structural precursors to form in a bounded environment before release, which translates into an expansion phase that inherits seed inhomogeneities at the right scales to promote early collapse. Observational discriminants are therefore crucial. A very low or absent tensor signal combined with specific shapes of non-Gaussianity, a hint of blue tilt confined to scales too small for the microwave background, but large enough for deep galaxy surveys, a pattern of spectral distortions in the microwave background, generated by energy released during a bounce or long loiter, and a distribution of tiny gravitational lenses that indicates an overabundance of very small halos would together compose a portrait that cyclic or emergent cosmologies could naturally paint. Conversely, a robust detection of primordial gravitational waves with a simple scale dependence and a lack of small-scale excess would lean back toward orthodox inflation with only modest amendments. The early dust and metals discussed earlier also play interpreter here. If cycles recycle, then grains or heavy elements cannot survive the high curvature bridge unless they are reduced to radiation and recreated, but the efficiency with which dust forms in each new aeon could depend on inherited parameters such as couplings within a dark sector, or effective constants reset by scalar fields that roll across cycles. Small lawful drifts in rates or couplings would then reveal themselves as systematic offsets in line ratios or in the relation between dust mass and metallicity at fixed time since the beginning, a pattern that next-generation surveys could test by building large uniform samples across redshift. A virtue of cyclic pictures is that they offer a reason for why the universe is so large and so flat without a single explosive burst, and a virtue of emergent pictures is that they provide time for gentle processes to sculpt seeds. A danger is that in providing time, they also provide room for anisotropy, or relics that must be hidden, and the very compactness of the earliest galaxies becomes a double-edged test. It demands seeds and smoothness both. The practical path forward is not to swear allegiance to a prehistory, but to use the earliest light as leverage on the preface. If confirmed compact abundances continue to strain single-field inflation with minimal features, while background measurements continue to allow only small tensors and reveal hints of particular non-Gaussian shapes, then the weight of evidence will tilt the scales towards cycles or emergent starts with specific parameter choices. If instead new data prunes the excess and smooths the misalignments, the cyclic horizons may recede into the realm of elegant possibilities. For now, the models stand ready to be weighed, promising that if beginnings are not singular, then ancient-looking structures may be less surprising because they would be echoes from a previous cadence carried across a bridge where physics changes costume but not character, and placed in the new act to set the rhythm before the audience even hears the first overt note. Shifting constants is a phrase that sounds like sacrilege because the laws that carry the universe forward are supposed to be stitched with thread that does not fray. Yet the earliest light invites a careful thought experiment in which the thread is still lawful but slightly different than assumed. The fine structure constant sets the strength of electromagnetic interactions and therefore controls how atoms space their spectral lines. The ratio of proton mass to electron mass shapes molecular transitions. The gravitational constant sets the pace at which matter gathers. The speed of light ties space to time and motion to causality. If any of these numbers drifted gently with environment or epoch, the visible consequences would be subtle but precise, and those consequences might ease the tension between bright compact galaxies at extreme distance and a conservative formation schedule. A slightly larger fine structure constant in the first few 100 million years would increase binding energies and shift atomic levels subtly, altering line wavelengths and cooling efficiencies in gas clouds. Molecular hydrogen, whose formation and cooling paths depend on both collisions and radiation, would assemble and shed heat with different timings, perhaps making collapse more efficient at lower densities. A slightly smaller proton-to-electron mass ratio would tilt vibrational and rotational lines of molecules, changing the way energy leaks from cooling gas. If meanwhile the gravitational constant were a little larger at high redshift, halos would deepen more quickly. Dynamical times would shorten and compact cores could form with less help from finely tuned inflows. The appeal of these ideas is not that they rewrite physics into a different language, but that they allow the same language to speak with a differently pitched voice for a short chapter. The discipline has long tested for such drifts. Spectra of quasars at intermediate redshift have been searched for centimetre-level shifts in rest frame lines that would betray changes in constants. Molecular absorption in damped systems has been compared with laboratory frequencies. Natural nuclear reactors in ancient terrestrial rocks constrain whether couplings changed on billion-year baselines. Atomic clocks in laboratories measure whether constants vary with time or with the gravitational potential of Earth's orbit. So far the verdict is that any changes must be small, but small is not the same as zero, and the earliest epochs are both more distant and more extreme than most existing tests. A lawful drift that vanishes by the time-light elements form, or that only turns on in environments with very high radiation densities or very low metallicity, could hide within present bounds, while still placing a thumb on the scale during the first rounds of galaxy assembly. The spectra already in hand can search for this thumb. When the near-infrared spectrograph and the mid-infrared instrument measure line centroids and relative spacings across a set of transitions with different sensitivities to the fine structure constant or to the proton-to-electron mass ratio, a coordinated offset that cannot be explained by motion, by calibration, or by blending could signal a drift. The test strengthens when several species are measured together because the pattern of shifts is a fingerprint rather than a uniform slide. Teams are building such fingerprint libraries and applying them to the most pristine spectra of high redshift galaxies and damped absorbers seeking deviations that are coherent across instruments and nights. The gravitational constant is harder to test directly with lines but it leaves other traces. The ages inferred from Balmer breaks at fixed redshift depend on the mapping between redshift and time, and a different mapping produced by a gently time-dependent gravitational constant would adjust those ages without moving lines. Strong lensing time delays would shift in a coordinated way across systems if the constant drifted, and the internal dynamics of early galaxies, when compared to their sizes, could be used as a consistency check. A tiny change might be enough to give compact objects more time to assemble without contradicting later observations, provided the change fades as the universe ages. An alternative to changing the constants that govern known interactions is to let a new field in a dark sector talk to ordinary matter in a way that depends on density or temperature. Imagine a scalar field that permeates space and whose value sets the masses of particles through a coupling that weakens as the density drops. In high-density, low-metallicity clouds where the first stars form the field, could tilt reaction rates, cooling curves, or opacities just enough to accelerate collapse and to change the ratio of massive to low-mass stars, while in later metal-rich environments the field would decouple, returning physics to the familiar values measured locally. The signatures of such a coupling would include slight anomalies in line ratios that trace excitation mechanisms, a different balance of elements produced in the earlier supernova, and perhaps a distinct relation between dust mass and metallicity at fixed age. Because the field would be smooth on large scales, it would not create obvious distortions in the cosmic microwave background or in nuclear synthesis if it disengaged early. It would speak mainly in the chemistry and structure of the first luminous objects. Tests for this kind of dark talk align with observations already underway. Line intensity mapping experiments that integrate the glow of many faint galaxies can measure the aggregate strength of oxygen lines and compare it to ultraviolet output at fixed redshift, searching for systematic shifts that hint at altered cooling. Stacked spectra can reveal whether the fraction of helium lines toward a stellar origin tracks metallicity differently at early times than at later times. The Atacama Large Millimeter Array can test whether the ratio of dust continuum to gas mass evolves with a slope that departs from local templates in a way that correlates with compactness. If these patterns appear with coherence across fields and with consistency across instruments, the pressure to consider a new coupling grows. A similar path runs through the possibility that the speed of light while fixed now might have been different when the universe was very young. Faster early light would change the horizon scale and the timing of recombination, while slower early light could alter the optical depth for ionizing photons to escape from compact galaxies. Such moving light must be managed with great care, because the harmony between the cosmic microwave background and baryon acoustic oscillations is sensitive to the propagation speed that threads the equations. However, within narrowly defined frameworks where a scalar field mediates an effective speed that relaxes to the current value well before recombination, the door is not completely closed. The observational handle would again be the alignment between ages inferred from spectra time delays from lenses and the redshift distance ladder built from standardizable candles. The ethics of proposing drifting constants or dark couplings require that every other systematic be exhausted first. Instruments must be cross-checked, wavelength solutions verified, skylines modelled, and line blending deconvolved. Only when a coherent pattern remains that cannot be erased by careful practice does the field earn the right to entertain altered rules. The posture is therefore one of curiosity rather than commitment. The payoff, if real, would be elegant, a universe that is still governed by conservation and symmetry, but in which a few numbers slide gently for a short interval, leaving atoms to cool, more easily stars to ignite with a slightly different mass distribution, and compact galaxies to appear without forcing simulators to contort every feedback loop. The price would be a reweaving of early history, so that terrestrial constraints, cosmic microwave background power spectra, and light element abundances remain in tune. The ease with which this reweaving could be done is uncertain, but the path is clear. Measure lines with enough precision to test fine structure runs and mass ratio drifts. Combine stellar ages with lens clocks to test gravitational pacing. Map chemistry and dust as functions of compactness to search for dark couplings that depend on environment. If nothing turns, the constants keep their crowns, and attention returns fully to baryonic craft. If something nudges the rulebook, grows a marginal note that says the earliest chapter plays with a slightly different key, and the harmonies that trouble the ear of theory become chords that the score can finally accommodate. Nearby certainty is the bedrock on which distant daring must stand, and the Space Observatory's honesty close to home has become a case study in how precision is earned rather than assumed. In the solar system, where geometry is known and motions are clocked by decades of ephemerides, the observatory's instruments learn humility and confidence at once. Asteroids sweep past with brightness changes that follow phase angles, predicted long before the observatory flew, and their light curves, sampled at cadences chosen to catch rotation, align with models that turn irregular shapes into flux as a function of sunlight and shadow. Comets flare as volatile ices sublimate, and the distribution of gas and dust around their nuclei imprints signatures in scattered light and in emission that match laboratory and spacecraft measurements of composition. Planetary rings present sharp edges, wakes and gaps that test point spread functions and stability. When a thin ring maintains its measured width across orientation changes and across temperature cycles, in the observatory the conclusion is not only that the optical train is steady, but that the reduction pipeline returns the same truth regardless of who runs it. The brightness ratios of ring and sail, which depend on scattering phase functions and particle sizes, repeat within quoted uncertainties from visit to visit, and when these ratios are compared with decades of photometry, from ground-based telescopes and from earlier orbiting observatories, they fall into place on the same curve. The observatory's detectors, which must count slow rainfalls of photons from ancient galaxies, are also asked to count bright familiar light without saturating or bleeding in ways that would contaminate neighbours or corrupt calibrations. This is not a trivial request at cryogenic temperatures in deep space. Dark currents are measured in the shadow between exposures. Persistence, the tendency for charge to linger in pixels after a bright event, is characterized by flashing stars and by internal lamps, and cosmic ray strikes which pepper the arrays with spurious steps are identified and excised by robust ramp fitting that matches expected rates. When those practices carry through to observations of satellites in the outer system whose surfaces have known spectral features, the match between measured band depths and laboratory spectra of ices becomes an independent endorsement that wavelength solutions and throughput are faithful. The near-infrared camera, which discovers the faintest smudges at the edge of time, also resolves craters jets and rings with a point spread function that is measured, not guessed, and that remains stable enough that an empirical model built from bright stars in one field can be used in another far away. Thermal breathing, the slow expansion and contraction of structures as the observatory warms in sunlight and cools in shadow, could have shifted focus or introduced minute astigmatism that would masquerade as compactness when measuring tiny galaxies. But in practice the measured focus drifts are small and predictable, and the reconstruction of the wavefront from guide star telemetry and from in situ focus sweeps shows that optical quality remains high, with variations that are removed by the dither and by the mosaicing strategies already in place. The mid-infrared instrument takes this steadiness into a regime where the glow of the observatory itself and the cosmic infrared background become relevant. By imaging known standard stars and well-characterized planetary nebulae, and by comparing the measured spectral energy distributions to models constrained by laboratory absolute calibrations, and by observational heritage, the instrument gains an absolute scale with uncertainties that are propagated faithfully. When it turns to bright solar system targets such as the thermal emission from the moons of the giant planets, the measured temperatures and spectral slopes fall within the expected range once surface roughness rotation and thermal inertia are accounted for. This is a check not only on detector response, but on the ability to separate instrument signatures from true sky signals in a wavelength range where scattered light and ghosts would be damaging if left unmodelled. The near-infrared spectrograph adds the crucial dimension of dispersion, and its veracity is tested by the sharpness and position of solar system lines, whose laboratory wavelengths are known to many significant figures. Reflected sunlight from planetary atmospheres carries absorption bands of methane, water, and ammonia that act as rulers. When those rulers measure the same across gratings and orders after correcting for the relative motion between observatory and target, the confidence that line centroids for faint galaxies are placed correctly strengthens. The microshutter array, a marvel of tiny mechanical doors, must open and close with reliability and must not imprint periodicities that modulate flux. When masks that select moving targets hold transmission steady as the object crosses the field, and when repeated mask patterns produce consistent spectra, the fear that the machinery could inject spurious structure fades. Cross-calibration binds local honesty to cosmic ambition. The Hubble Space Telescope overlaps with the Space Observatory in near-infrared filters, and stars observed by both define color terms and photometric zero points, whose differences are stable and small. The Atacama Large Millimeter Array observes thermal dust emission and spectral lines from gas in nearby disks and comets, when the Space Observatory's mid-infrared maps of the same targets predict far-infrared behavior that the millimeter array confirms the circle closes. The Subaru telescope contributes deep optical imaging and spectroscopy that anchor ground-based calibrations of atmospheric lines and telluric corrections, and when those anchors are used to tie the Space Observatory's fields to an absolute astrometric grid, the positions of faint sources shift by amounts that are consistent with the measured proper motions of reference stars. This chain of agreement is not cosmetic. It means that the photometric scales point spread functions and wavelength solutions that define the earliest galaxies are the same scales, shapes, and solutions that successfully describe objects that do not permit creative interpretation. The instrument team and the wider community hunt for subtle failures anyway. They test whether the measured sizes of bright, unresolved stars drift with time or with the angle between the observatory and the sun, and they find no drift beyond the quoted error bars. They test whether background subtraction leaves low-level gradients that could bias surface brightness profiles, and they design dithers and sky frames that cancel those gradients to below the level that would matter for compact high redshift sources. They test whether small pointing drifts during exposures smear images in a way that makes objects appear smaller, and they correct the drifts by reconstructing pointing from fine guidance sensor telemetry. They test whether the detector nonlinearity at the bright end leaks into the calibration of the faint end, and they calibrate the response across orders of magnitude in flux using standard stars with independently measured spectra. The result of this stubborn skepticism is that each local success becomes a reason to trust a distant measurement a little more, and paradoxically that trust heightens the tension when the distant measurement strains expectation. When a compact galaxy at redshift 10 appears barely resolved, the fear that a soft point spread function or a breathing focus made it look smaller has already been retired by the way rings and stars behaved. When a Balmer break suggests an age that nibbles at the available time, the worry that a wavelength miscalibration slid features into place is undercut by the way methane bands agreed in the atmospheres of the outer planets. When mid-infrared excess implies dust that should not yet be plentiful, the suspicion that detector artifacts inflated flux is weakened by the way moons and nebulae trace the same absolute scale question after question. Local clarity amplifies distant doubt because it removes easy exits. The ruler is straight where it can be checked, so the crookedness in the early story belongs to the story. This is not a verdict in favor of anomaly. It is an instruction to look for missing physics or for blended causes that combine to mimic improbable youth or improbable maturity. The observatory's honesty close to home frees theorists and modelers to spend their capital on mechanisms rather than on excuses, and it encourages observers to push deeper and to risk bolder programs because they are not fighting their tools. In this way, the planets, the comets, the rings and the asteroids have become quiet collaborators in the exploration of the first light. They have served as mirrors, as rulers, and as tuning forks, and by ringing true they have made the dissonances that remain in the deep sky stand out in cleaner relief, turning intrigue from suspicion into a legitimate question about how the universe wrote its opening pages. The community reacts in a cadence that mixes excitement with audit, and through late year 2024 and into year 2025, the conversation becomes a living laboratory where claims are advanced, revised, and sometimes withdrawn with a frankness that signals health rather than confusion. Preprints surge first because speed matters when a fresh image or a new spectrum rises above the noise, and the earliest manuscripts push number, counts of compact sources high, interstellar masses that press into regimes once reserved for later epochs, and sketch-age distributions whose Balmer breaks imply cycles already completed. Within weeks, counter-analyses appear that remeasure photometry with alternative background models, replace simple screen dust with mixed geometries, alter priors on the initial mass function and on star formation histories, and emphasize that extreme equivalent widths can flood broadband filters and mimic continuum. Some luminous candidates dim under this scrutiny, a few vanish into blends, and a handful grow more secure their lines and break surviving surgeries that would have exposed careless stitching. The tone shifts from proclamation to triangulation. Teams share cutouts, model grids and codes with rivals, and rivals respond in kind, building cross-checks that trade ego for accuracy. Where disagreements persist, they are mapped rather than denied. One group's mass estimates depend on a particular choice of stellar library. Another group prefers a library that handles low metallicity at very hot temperatures with different opacities. The two choices are not reconciled by rhetoric, but by targeted spectra that aim at the lines most sensitive to the disputed physics, and by laboratory and theoretical work that updates the libraries themselves. Conferences become staging grounds for live recalculations. A presenter shows a size distribution measured with forward modelling. A questioner notes that the point spread function wings in their reduction are slightly broader at certain roll angles. The presenter runs the fit on the questioner's model during the coffee break and returns with a revised slope that moves but does not collapse. In parallel, retractions and revisions occur without drama. A claimed helium line that hinted at primordial populations is withdrawn after a deeper exposure shows that a sky residual crept into the extraction. A lensed source that seemed astonishingly compact is reassigned a modestly higher magnification after an updated mass model includes a satellite galaxy that had been ignored, and the compactness relaxes from breathtaking to merely impressive. These episodes are not treated as scandal. They're treated as housekeeping in a laboratory that finally has the light to see dust on the bench. Review articles begin to weave order. They catalogue which trends are robust to pipeline choices and which are fragile. They quantify how much mass and size estimates move under conservative changes in priors, and they propose a vocabulary of confidence that avoids the binary of confirmation and refutation. Catalogue papers start to include provenance tables that list for each object the surveys in which it appears, the reduction cultures that have measured it, and the degree of agreement among them. This meta-information becomes as valuable as a new detection, because the path a result has taken through multiple hands is now part of its weight. At the same time, new instruments and surveys report results that touch the same puzzle from oblique angles. Measurements of the kinetic Sunyaev-Zeldovich effect tighten limits on very early, very extended reionization, making it harder to push all of the infrared excess into exotic early populations. Weak lensing maps sharpen and reveal substructure in clusters used as cosmic telescopes, raising confidence in magnification fields that underpin several of the most extreme claims. Intensity mapping experiments release power spectra of aggregate line emission that can be folded into models of star formation efficiency at high redshift, and while the error bars are wide, the central values lean toward a universe where early compact systems are not flukes. This is enough to keep the community from withdrawing into caution. Instead, observing proposals grow more surgical. Teams coordinate to obtain joint coverage of the same sources, with the near-infrared spectrograph at multiple dispersions, with the mid-infrared instrument for warm dust constraints, and with the Atacama Large Millimeter Array for cold dust and gas, so that energy budgets can be closed rather than inferred. Time is allocated to repeat observations at different roll angles to probe systematics in background subtraction and in contamination from neighbours. Parallel fields are planned so that serendipity is domesticated into strategy. Simulation groups respond in public. They open repositories, post blind forecasts for specific survey footprints, and accept the risk that a wrong prediction will be remembered. When a blind forecast lands near the data without excessive parameter tuning, trust rises. When it misses, the post-mortem becomes a lesson in the physics of compactness, dust yield or feedback porosity that others can use. A cultural shift becomes visible. Graduate students present talks that include live notebooks. Senior scientists submit addenda that correct their own earlier claims. Journal clubs celebrate careful null results that prune parameter space. There is still competition, but the prizes become a shared map rather than a solitary flag. Even the language of debate grows more precise. Words like anomaly, crisis, and tension give way to phrases like posterior shift selection, coupling, and model identifiability. This is not an evasion. It is an insistence that the disagreement be engineered into quantities that can be measured. Through all this, a few through lines remain. First, the abundance of compact luminous galaxies at redshifts beyond 10 holds up when spectroscopic confirmation is available, though the extremes soften at the margins. Second, spectra that show Balmer breaks and moderate heavy element lines continue to argue for earlier cycles of star formation in at least a subset of sources, even after dust and line contamination are modelled carefully. Third, mid-infrared and millimeter observations confirm dust in some of these systems, at levels that are difficult to explain without quick grain growth or efficient survival in the aftermath of early supernovae. Fourth, gravitational lensing remains a helper rather than a villain. It enhances counts and reveals otherwise hidden structures, but magnification maps refined with stellar kinematics and with weak lensing do not support a conspiracy of widespread strong boosts that would erase the headline. Against these several moderating influences gather strength. Burstiness and duty cycles can bias samples toward phases when galaxies are both brightest and smallest. Selection linked to surface brightness can hide a population of larger dimmer systems. Photometric redshifts for the faintest candidates remain vulnerable to priors that are difficult to justify in an era of rapid discovery. The community's mood, therefore, is not a swing between triumph and retreat, but an equilibrium that leans forward. The field has entered a phase where the speed of correction is as important as the speed of claim, where the durability of a result across pipelines counts as much as the novelty of the object, and where the shared aim is to turn intrigue into measurement by refusing both hype and cynicism. The reaction in some is a choreography of skepticism and hope, a willingness to rewrite figures while keeping faith with data, and a recognition that consensus that shifts without settling is not a failure, but the expected motion of a science that has just opened a new window and is letting the air change the room. Toward an open edge, the field moves with proposals sharpened into tests, and with new observatories entering as adjudicators rather than bystanders, so that the next pages of the story are written less by broad claims and more by experiments that choose between timelines and new physics. Upcoming cycles of the James Webb Space Telescope are designed like careful cross-examinations. Teams will reobserve the same compact galaxies with deeper dispersions on the near-infrared spectrograph to isolate age-sensitive features that separate truly old populations from young dusty ones, and they will pair those spectra with mid-infrared measurements from the mid-infrared instrument that tighten the energy budget by forcing absorbed starlight to reappear as thermal glow. Programs will deliberately target fields with overlapping coverage from different deep surveys so that the same objects are measured under distinct reduction cultures, and so that confidence grows from convergence rather than from charisma. Gravitational lensing fields will be revisited with additional roll angles to peel away contamination and to fix magnification with pixel-level reconstructions tied to stellar kinematics in the lenses, turning each cluster into a calibrated balance on which the brightness and sizes of the earlier sources can be weighed without generous assumptions. Time domain strategies will expand because clocks are as persuasive as colors. The community will monitor lensed supernovae and active nuclei to extract time delays that test the expansion history, and will use those same delays to refine mass models that underpin claims about modest or strong magnification. If the expansion pace inferred from lenses shifts toward ages that ease the crowding of early structures, the pressure to revise rules will relax. If not, the tension will stiffen into a demand that baryonic craft alone show how to reach the observed compactness and mass. The Nancy Grace Roman Space Telescope will join as a wide-field partner whose sharp imaging and slitless spectra can conduct a census across areas large enough to tame cosmic variance. Roman will harvest thousands of candidates at redshifts beyond 10, deliver homogeneous size distributions and map weak lensing shear with a fidelity that binds magnification fields to theory. By overlapping its fields with those of the James Webb Space Telescope, Roman will allow cross-calibration of photometry and morphology at the scale where population statistics become tyranny for models that survive on small numbers. The Euclid mission, with its optical and near-infrared view and its weak lensing expertise, will supply complementary depth and area tracing the growth of structure from later times into the dawn, and tying the small scales probed by deep fields to the large scales that set the background against which faint misalignments were noticed. Together, Roman and Euclid will sketch the scaffolding on which the earliest lights hang, and will challenge any explanation that works only on postage stamps but fails on maps. On the ground, the Veresi-Rubin Observatory through the Legacy Survey of Space and Time will paint the time axis with long, even strokes, catching supernovae and tidal flares across vast volumes, some of which will be lensed by chance into useful clocks. Rubin will also assemble the low-surface brightness outskirts of galaxies and clusters, constraining intra-halo light that may contribute to the cosmic infrared background. The extremely large telescope, the Giant Magellan Telescope and the 30-meter telescope will train adaptive optics, sharpened eyes on the kinematics of compact sources, resolving velocity fields and line widths that anchor dynamical masses and that reveal whether gas is flowing calmly into deep wells or exploding out along channels carved by feedback. The Atacama Large Millimeter Array will deepen its role as the auditor of cold dust and gas-resolving carbon lines and dust continuum at resolutions that match or surpass the sizes inferred from near-infrared images, and thereby testing whether the compact light is matched by compact fuel or whether geometry conspires to make small radii from distributed reservoirs. Upgrades in bandwidth and baselines will push the array into regimes where the faintest highest redshift sources can be mapped directly rather than stacked. Intensity mapping will rise from promise to practice. Experiments that integrate the collective glow of spectral lines such as singly ionized carbon and doubly ionized oxygen across wide fields will measure the aggregate strength of early star formation without waiting for every source to be resolved. The power spectra and the cross-correlations of these intensity maps with weak lensing convergence and with galaxy catalogues will act as global checks on any claim about rapid early growth. If the integrated line power is high, the excess must be paid for in photons and metals. If it is low, then selection and magnification must carry more weight than they have so far. The square kilometre array and its precursors will map the neutral hydrogen of the intergalactic medium during reionization, measuring the patchiness and timing of the great transition from neutral to ionized gas. Those maps will be cross-correlated with the locations of compact bright galaxies from the James Webb Space Telescope to test whether these objects truly drive early bubbles or whether they sit in environments that are not yet cleared, which would force a reconsideration of their escape fractions and their role in cosmic timelines. Meanwhile, experiments that hunt for gentle distortions of the frequency spectrum of the cosmic microwave background will search for the fingerprints of early energy release, or for the collective heating effect of tiny structures offering a high-level constraint on any scenario that seeks salvation in altered beginnings. The program of tests will also reach into laboratories and into codes. Stellar libraries will be extended to hotter lower metallicity regimes with updated opacities and atmospheres, so that spectra fitted to galaxies at the edge of time are grounded in physics rather than in extrapolation. Grain growth models will be run under conditions that match the inferred densities and radiation fields of compact star-forming knots, and the yields of supernovae across progenitor masses, including the rare pair instability channel, will be recalculated with attention to how much dust survives reverse shocks. Simulations will publish blind predictions for exactly the fields and selections used by observers, with point spread functions, sky backgrounds and reduction pipelines mirrored in synthetic data, so that the comparison is no longer a negotiation but a test. If familiar physics can reproduce not only number counts, but also the joint distribution of sizes, line ratios, dust fractions, and variability in compactness, the case for timelines without new rules will strengthen. If a small but durable gap remains, curiosity about additional fields, shifting constants or echoes from an earlier phase will harden into need. The choreography of this next movement is to braid narrow beams and wide maps to measure time delays and spectral breaks, while integrating line power across thousands of square degrees and to insist that every proposed resolution appear in more than one language of evidence. The edge that the field approaches is open not because it is vague, but because it has many doors. One door leads to a universe that learned to build fast using known tools pushed to their limits. Another opens onto modest amendments that tilt the odds without rewriting the code. A third reveals that the preface of the cosmos had more notes than the overture preserves. The readiness to walk through the door that the data unlock, and not the one that preference paints, is the character of the community now. Intrigue therefore lands softly, not as drama, but as an invitation to finish the measurement. The earliest light will either settle into the schedule once all the budgets are closed and all the clocks agree, or it will keep a small remainder that asks for a new term. Either outcome will have been earned by instruments that tell the truth nearby, and far by teams that trade pride for precision, and by a plan that turns wonder into work. The room is dark and gentle, and the sky feels nearer now, not as a vault but as a slow breath, and the earliest light that seemed so distant has become a kind of quiet company, a set of small certainties and softer questions that rest together without needing to win. Instruments that learned honesty on rings and comets have carried that honesty into the far past, and the galaxies that look too bright and too compact have not vanished under scrutiny, though their edges have softened where caution asked for it. Dust has arrived early, but not rudely. Lines have whispered of cycles already looped. Clocks have tested the calendar with an even hand, and simulations have stressed their frames without breaking, hinting that familiar physics still has room to bend toward speed. Theories have opened doors without slamming others from echoes that adjust the overture to constants that might have hummed in a slightly different key for a short while, and the wide surveys that are about to begin will ask the same questions from farther back and from much farther to the side, turning deep fields into context and context into test. If the schedule holds, light will anchor, light budgets will close, and time will keep the pace that background maps set. If the schedule asks for an extra term, the term will be small and earned a measured note rather than a flourish. For sleep, that is enough. The universe is not hurried, it is careful, and careful stories do not end. They lean forward with the grace of things that are still true tomorrow. Allow the mind to loosen, and let the earliest galaxies become dim lanterns in a soft corridor, steady and unthreatening, marking a path that does not need to be walked tonight. In this corridor, questions are pillows and answers are blankets, and the distance between them is warm. Rest inside that distance. The stars will keep the watch.